Welcome to my second lesson on combinatorics. This lesson's on sum and product rules. We saw examples of those in my first lesson. I'll go in a little bit more detail here. And then the pigeonhole principle and several variations of that principle. On this slide I have two of the more basic rules for counting. The first one is called the sum rule. And in this case you have let me point to it. We have an event can happen in m ways, and another event can happen in n ways, and only one of the two events can happen at a given instance. Then there are m plus n ways for the two events to happen. So I gave an example here of a die in a car. So only of a card draw, I should say. So there's only one of the two can happen, and we want to know what's the total possible number of ways of the combination, and that would be adding the 6 possible rolls of the die and the 52 possible draws for the card, and so you get a total of 58 possible outcomes. Okay, that's a little bit unusual in the sense, but I just want to emphasize here, only one of the two can happen. Either you roll the die or you select the card, and so there's altogether 58 possible outcomes. And we can extend this to R events, where the ith event has m sub I ways of happening. And in that case, we just add m sub 1, m sub 2 up to m sub r. In this case, the events are said to be mutually exclusive. So only one, if one happens, then the other ones cannot. So just take another example. Let's say we had 7 dice, each one was a different color, and we wanted to know what were and you can only roll one, so you have to pick one of the dice and then roll it, and so you get a number and the associated color, and so that would be 6 plus 6 added together 7 times, or 42 possible outcomes. Then we have a very similar rule called the product rule. If a task consists of a sequence of choices where the first stage can be done in m ways and the second in n ways, regardless of the first choice, then the total number of possible outcomes is m times n. So if we use the die and card drawing example, we would do both of them in this case. So you'd have 6 outcomes for the die roll and then 52 outcomes for drawing the card from the deck of cards. And so you would get 6 times 52, or 312 possible outcomes. And again, we can extend this to R events, where the ith event can occur in m sub I ways, and then the total number of outcomes is just m sub 1 times m sub 2 times m sub r. If I took the example of the 7 dice of different colors, and we wanted to know what was the total possible number of outcomes where the color made a difference, we wanted to take that into account, then we would have 7 to the 6th power, and 6 to the 7th power, right? 6 possible outcomes, multiply times itself 7 times, so that would be 6 to the 7th is the total possible number of outcomes. This is the simplest case of the pigeonhole principle that I'm mentioning here. If each item in a set of n items, call it set 1, is to be associated with one item in another set, call it set 2, where set 2 has m items and n is greater than m, then at least one item in set 2 must have more than one item associated with it from set 1. So this is sort of a variation of what I had mentioned on my first lesson, where I talked about pigeonholes and pigeons and containers and putting balls in containers. So let's try to make this a little more concrete with an example. If you put 10 balls, so that would be our set 1, and we want to associate them with 9 boxes, then clearly one of the boxes must have 2 or more balls. So it seems very simple, but sometimes it's not obvious how or when it can be applied. So I have an example here, and I'll give you the solution on the next slide. Suppose that you have a collection of many red marbles, blue marbles, green marbles, and white marbles in a box. What is the least number of marbles that you need to retrieve from the box while not looking? So you're kind of closing your eyes, you have a blindfold on, you're reaching your hand into the box. And the question is, what's the least number of marbles you need to pull out to be sure of getting 2 marbles of the same color? Okay, so I'll let you think about that, and I'll give you the solution on the next slide. Oh, here's my solution. I tried to map it to the definition of the pigeonhole principle. So I let the 4 colors be the pigeonholes. So that's our set number 2, and n would equal 4 in that case. And we're being asked to find the smallest number of n such that we are sure to draw 2 marbles of the same color. So that one can view set 1 as the number of draws. The smallest value n to ensure the desired result is 5. So that would happen, worst case would be where you draw, in some order, it doesn't matter the order I listed here, but in some order you draw red, blue, green, and white in the first 4 draws. And then on the 5th draw, you have no choice, you run out of colors, you have to pick one of these 4 colors on the 5th draw, and that guarantees that you have a match at that point. Pigeonhole principle generalization number 1. So if each item in a set of k times m plus 1 items, we'll call this set 1, is to be associated with one item in another set, call this set 2, that has m items. So you have more items in set 1 than set 2. Set 2 is sort of the containers, and set 1 are the pigeons or the balls or the marbles or whatever that you're associating with the second set. So in this case, then at least one item in set 2 must have k plus 1 items associated with it. So let's look at an example. Let's set S1, set number 1, consists of 31 balls, so it's k is 3 and m is 10. And set 2 has 10 containers. Then the generalized pigeonhole principle tells us that at least one of the containers must have k plus 1 equals 4 balls. And you can see it here. If we have 31 balls and we're trying to avoid having 4 balls in any one of the containers, the best we can do is put 3 in each one of these 10 containers. And then when you get to the 31st ball, this one out here, no matter where you put it, you're going to have 4 balls in one of these containers. So that's what this principle tells us here. Okay, so on the next slide, I'll give you an exercise to look at related to this generalization, and then after that, there's yet a second generalization of the pigeonhole principle that I'll talk about. So here's our example. Consider example 1 regarding the box of marbles. You remember we had 4 different color marbles, and but this time determine the least number of draws that are needed to ensure at least 5 marbles of the same color. Okay, so I'll let you think about that, and then I'll give you the solution on the next slide. So to solve this problem, we use the pigeonhole principle generalization number 1. We want k plus 1 equal 5. We want to eventually have the 5 balls in one of the 5 marbles in one of the containers. So k is equal to 4. Further, as before, with our first version of this problem, m equals 4. So we have k times m plus 1, and that's 17. So the solution to the problem is 17 draws are required to ensure at least 5 marbles of the same color. Right, so that might be a little bit dense, although I wanted to fit it into the principle here, but maybe a picture is a little bit easier. So we have green, blue, yellow, and red balls, and we want to have what's the minimum number of balls to draw out so that we have at least 5 of one color in one of the containers. So the way we look at it is we try to avoid having the 5 balls of one color in a container. And what's the best we can do? Well, the best we can do is, and I guess this is highly improbable, but the best we could do is we draw in the first 16 draws, we draw 4 green, 4 blue, 4 yellow, and 4 red. It could be in any combination, but they have to go into these containers as shown here. And then when you get to the 17th draw, there's no other possibility that one of the whatever color ball you draw out is going to be the same color as one of the either green, blue, yellow, or red. So that's the minimum number of draws is 17 in that case. And you can see how to up this. If you wanted to know what's the least number of draws to get 6 balls in one of the containers, then of course you would have 5 here, 5 here, 5 here, and 5 here. Again, it'd be very improbable, but you would have 25 draws where you'd have 5 of each, and then the 26th draw would force you to have 6 balls of the same color. So you can see how this works. All right, so let's continue. We have one more version of the pigeonhole principle, generalization number 2. If there are a sub 1 plus a sub 2 plus ... plus a sub n minus n plus 1 or more items in a set, we'll call that set 1, to be associated with n items in another set, we'll call that set 2, then there exists a number j from 1 to n such that item j has a sub j or more associations with items in set 1. So one way to look at this is to think of set 2 as being containers, and their occupancy is shown here. A sub 1 minus 1, a sub 2 minus 1, and so forth, all the way up to a sub n minus 1. So we're staying just below the threshold to this claim here, that at least one of them has a sub j items in it. So we're just below the threshold. This is the best we can do. And then if we add one more, which would give us this number here. You notice if you add all these together, you get this quantity here, which is just one less than this. So if you're forced to add one more, then at least one container, say j, has a sub j items. So we can prove that. I sort of proved it here, but we can prove it a little more formally. Assume to the contrary that for every j from 1 to n, item j in set 2 has at most a sub j minus 1 associations with items in set number 1. Summing the number of associations, we get this quantity here, but this is 1 less than the number of items in set 1, all of which were assumed to be associated with an item in set 2. Thus we have a contradiction, and our contrary assumption is false, so there must exist some j from 1 to n such that the item j in set 2 has a sub j or more associations with items in set 1. Okay, so let's look at an example on the next slide using this as a solution to the problem. So here's our problem. If someone wants their pocket change to have at least 4 half dollars, or at least 8 quarters, or at least 20 dimes, or at least 40 nickels, what is the least number of coins this person needs to select from a jar of coins, assuming there's, say, over 100 of each type, so you don't run out of any of the coinage. Another way to state the problem is to ask, what is the least number of coins that needs to be blindly selected from a jar of half dollars, quarters, dimes, or nickels to ensure $2 in change of any one of the 4 particular coinages? Okay, so if you want to give it a try, pause here. Otherwise, I'll give you the solution on the next slide. So we're going to use the Pigeonhole Principle generalization number 2. We'll let n equal 4. So that'll give us 4 containers, so to speak. That'll represent each container will represent a different coinage. Then A1 will be 4. That's the number of half dollars you need to make $2 and change. Then A2 is the 8. That equals the number of quarters. A3 is 20. That's the dimes. And then A4 represents the nickels. We'll set that to 40. And then we just use the formula for this generalization. We plug everything in there and we get 69. So 69 is the minimum number of selections from the coin jar to ensure $2 in change of at least one of the coinages. So another way to look at it, this is sort of a worst case analysis. You want to avoid having $2 in change in any one coinage. How far can you go before you cross the limit and you're forced to have $2 in at least one of the coinages? So you could have 3 half dollars, right? That gives you $1.50, and then 7 quarters, so that's just short of $2. 19 dimes, $1.90, and then 39 nickels. So you could draw all those out, and that would be a total of 68 coins, and you would still not have $2 in any one of these coinages. However, the next coin you pick has got to be either a half dollar, a quarter, a dime, or a nickel, in which case you would then be forced to have $2 in change in one of the coinages. Okay, so kind of two ways of looking at it. This is more formal using the formula, and this is more of a worst case analysis. But the formula is really derived from a worst case analysis, so in a sense it's the same type of solution. Okay, so that's the last slide in this lesson. If you like this lesson, please give it a thumbs up. I'll have a few more lessons on combinatorics, so stay tuned.